Hello everyone, my name is Partho Das, Assistant Professor, Department of Electrical Engineering, JS College of Engineering, West Bengal, India. Welcome to my class. So today's topic is single phase induction motors double revolving field theory. So it is a very important topic because as we know that single phase induction motor is a not self starting machine, so we have to give some external force to make it start. So why it is not self starting machine? So what is the funda behind that we are going to discover today. So let us start. Okay, so types of, so before starting the concept of this double revolving field theory, the first let us check what are the types of single phase motors are available. The single phase motor which are designed to operate from a single phase supply are manufactured in a large number of types to perform a wide variety of useful services in home, offices, factories, workshop, in a business established, etc. Small motors, particularly in the frictional kilowatt sizes, are better known than any other. In fact, most of the new products of the manufacturers of space vehicles, aircrafts, business machines, and power tools, etc., we have possible due to of the advances made in the design of frictional kilowatt motors, since the performance requirements to the various applications differ so widely. The motor manufacturing industry has developed many different types of such motors, each being designed to meet specific demand. Single phase motors can be classified as under depending upon their construction and method of starting. So there's the induction motors, repulsion motors, AC motors, and unexcited synchronous motors. So there are different types of motor. So within that we are coming to the single phase induction motor. So constructionally this motor is more or less similar to the polyphase or three phase induction motor. So it has a stator part, it has a rotor part. uh, in the rotor case, in case of three phase induction motor, we have uh, two types of winding, that are two types of construction. One is the squirrel cage and second one is the slip ring. But in case of induction motor, we usually use the squirrel cage induction type rotor in case of single phase induction motor. Now in three phase induction motor, we know that due to the presence of this three phase, there is a generation of rotating magnetic field. So that's why that single phase induction motor is a self starting machine. But in case of single phase induction motor, it is not a self starting machine. Okay, so why it is not self starting machine? So that funda actually we can explain by this two double root field theory and by the cross field theory. So let us let us check what is the double revolving field theory. Yes, this is. So double field revolving theory. So this theory makes use of the idea that an alternating uniaxial quantity can be represented by two opposite rotating vectors of half magnitude. Accordingly, an alternating sinusoidal flux can be represented by two resolving fluxes, each equal to the half of the value of the alternating flux, and each rotating synchronously in opposite direction. For example, a flux given phi is equal to phi max cos 2 pi ft is equivalent to two fluxes revolving opposite direction, each with a magnitude of half of phi m and an angular velocity of 2 pi f. It may be noted that Euler's equations for cos theta provides interesting justification for the demonstration of a pulsating flux, and its expression is given by cos phi is equal to half e to the power j theta plus e to the power minus j theta. where this term e to the power j theta represents a vector rotating clockwise through an angle theta, whereas this minus j theta represents the rotation in the anticlockwise direction. Now the above flux equation can be rewritten like this way. See, what is the expression? Phi is equal to phi m cos 2 pi ft is equal to phi by 2 e to the power j2 pi ft plus e to the power minus j2 pi ft. Now the right hand expression, so this is okay, this thing is a very interesting and very wonderful representation how the double Revolving field theory is working. So for the simplicity, follow my pointer very carefully. We are considering that the total flux is phi, and now that flux is divided into two sections, one phi by 2 and phi by 2. So once we follow my pointer, we are considering this is a one flux, a flux that is have a value of phi by 2. There is a flux b that has a value of phi by 2. This a flux is rotating in this anticlockwise direction, and this b flux is rotating in the clockwise direction. So now we are going to check at the different point what is the value. So we can say that if these two are the um, vectors of this flux, so the resultant will be here, that is phi n definitely. Now this A is rotating in anti-clockwise direction and the B is rotating in the clockwise direction, so they are shifted. So the second location, as you can see over here, this is this one. So now the A location is here and the B location is here. So now with this horizontal axis we have an angle. What is the angle? This theta. So what is the resultant of these two vectors? The resultant is the phi n cos phi, correct? So now again it is moving, now coming to the picture number 3, it is again moved to this location. Now A is this location, B is this location. So what is the value? Okay, so what is the value? It is again, we can say that is phi m cos phi. Now what is the angle? 90 degrees. So cos phi 180 degrees, so that is equal to 90 degrees is equal to 0. So it is at that time, so no EMF is induced. So like this way, when it is in the opposite, so now again A is rotated, B is rotated, so now again they are in the opposite plane. So it has now at that time it has a value of minus 5, as we can see in the diagram. So that means what we have done, we have rotated this flux in this direction, A flux, in B flux rotated in the clockwise direction. So at different instant we have find it out what is the flux value. Okay, so now if we do that, and if we divide that, and if we analysis everything, then we can find out if the value of this phi m is representing a sinusoidal waveform. See, this is the maximum sinusoidal value. Okay, so we can start from here, we can start. So if this is the xy axis, so from the y axis maximum point it is going to be start, because it is at the phi m. Now it is decreasing in between this maximum to the minimum, where it has a zero value. In between somewhere we are considering this is phi m cos phi, and this the picture number C is representing that is at the zero location. Now this is it is going in the negative half. Yes, it is going the negative half, because see, this it is going for the negative maximum, that is minus phi m. So like this way continuously it is rotating, and it is making like this sinusoidal waveform is generated. Okay, after some time, when A and B with rotate through angle theta and theta plus and theta minus, the figure is whatever I am telling to you, that thing is written over here. So different instances are given, what I am telling to you. So yes, that yes, this picture I am telling to you. So from, if we consider the very carefully, follow my pointer, if we consider this picture number 1, then it is the generation of flux value is this one. If we consider the picture number 2, we can consider the maximum and minimum value in between somewhere, some value, because that is known to us. So picture number 3, it has again the zero value. So sorry, this is coming to the 0. Okay, so picture number D, here it has a value but negative maximum. So like this, from here it is started, it is going like this, and there is a negative maximum. Okay, so next value should be it again going to be 0, it should be correct. So yes, now if we do that, see, it is only reverse case. Now A location and B location is reverse. Okay, so that means again there is a 0. So again there is a 0. Like this way continuously it is going to rotate, and it is generating sinusoidal waveform. Okay, now it may be noted that as it is a single phase induction motor means that rotors, the motor has some slip. Okay, so what is the slip formula? Slip formula is given by ns minus n by ns. Okay, so again we can write down from that, we can rearrange the equation like that, 1 minus n by ns. Okay, so or we can write down n by ns is equal to 1 minus s. With respect to the forward rotating flux, okay, then the slip with respect to the backward rotating flux is 2 minus s. That is, see, first case we are considering, follow my pointer. This is the uh, this slip value is for the forward slip, and this is for the backward or reverse flux. For that we can consider that what should be the value of this slip. So there we can find out that is equal to 2 minus s. Okay, so if we think sorry, so if we these are the two sleeves values, so if we consider that too, so here it is a very interesting characteristics curve is there. So what is there in the characteristics curve? So that is the slip versus torque characteristics curve is there. So now if we think of that, so here in the x-axis we are considering this slip, and in y-axis we are considering the torque. So at the center the slip has a value of 1. In the right hand end we have a slip value is 0, and the left hand end we have slip value of 2. Okay, so now for the forward slip the characteristics will be like this way. Follow my pointer. For the forward slip the characteristics between slip and torque is this. For the backward slip the torque slip characteristics will be this. As we are considering it is a double benefit, so we are considering two components. So this is the upper one is the forward slip, and this one is the backward or reverse slip. So what is the resultant? In between that two is the resultant, this one is the resultant. Clear? So that means we have a forward slip, we have a backward or reverse slip, and with respect to torque we can plot that in the graph paper. Okay, and we are considering that the forward due to this forward slip there is a torque generation which has a direction in clockwise, and reverse slip has a direction in the anti-clockwise. So like this way, so each of the components of the flux will revolving the stator cuts the rotor, induces an EMF, and this produces its own torque. Obviously that two torques called forward and backward torques are oppositely directed, so that there is no rate result is required. Torque is equal to their difference as shown in the figure. Okay, so here is some mathematical expression. Now in an induction motor it is seen that the induced EMF in the rotor decreases from its standstill value of E2 and AC2 when in rotation. Obviously the difference 1 minus S, E2 is the EMF called force by the rotation of the rotor, similar to the back EMF in DC motor. Hence gross mechanical power developed in the rotor is given by the product of the back EMF, armature current, and rotor power factor. Okay, so the mechanical power developed is given by 1 minus s into E2 into I2 cos phi 2. Now what is I2? I2 in case of single phase induction motor when it is at running condition. So see, basically those things we have already discussed in three phase induction motor chapter, how to derive the equations. Okay, so I2 is basically AC2 by uh, under root r2 square plus sx2 whole square, and cos phi 2 we know that r by z, so here it will be r2 by z2. What is z2? Again it is under root r2 square plus sx2 whole square. Okay, so now we know in this particular equation I2 value, and in this, follow my pointer, this is the particular equation. In that equation we know the I2 value, and now we know the cos phi 2 value. So just put over here. So what is actually we are getting, that is s into 1 minus s e2 square into r2 by r2 square plus sx2 whole square. Okay, so now for the calculation purpose, multiplying the numerator and denominator by s, we will get 1 minus s by s into r2 plus s square into e2 square by r2 square plus sx2 whole square. Okay, so where this s2 square, this e2 square uh, by e2 se2 by r2 square plus sx2 is equal to I2 we know, so we can replace that in the equation and we can find out like this way, that is um, 1 minus s by s into I2 square into r2. So we know that I2 square r2 is a loss, copper loss, rotor copper loss per phase, so we can derive from there rotor copper loss by rotor output is equal to s by 1 minus s. That those everything we have done in three phase induction motor, so those things again I am discussing with you as we are doing the same things over here. Okay, now the power developed by a rotor, the gross power developed, that is 1 minus s by s into I2 square into r2. So if the n is the rotor speed in rps, the torque is given by, that is generated gross power input, that is pg by 2 pi n. So if we take the 1 by 2 pi n common, then that pg is equal to, already we have find it out, that is 1 minus s by s into I2 square into r2. Now rotor speed n is equal to, we know that ns minus ns into 1 minus s. So now for the Tg, the gross torque equation is given by 1 minus 2 pi ns into 1 minus s into 1 minus s by s into I2 square into r2. So now here from there particular equation, 1 minus s, 1 minus s will be cancelled out. So the remaining equation will be 1 by 2 pi ns into I2 square into r2 by 2. So if we consider the if we consider that 1 by 2 pi ns is a constant term for a particular single phase induction motor, then we can consider that is equal to k, and then the equation becomes k into I2 square r2 by s. So hence the forward and backward torques are given by Tf is equal to k I2 square r2 by s, and Tb, that is the backward torque or reserve torque, different names are there, is equal to minus k I2 square r2 into by, not here we will not going to use this only the slip. So what is the backward torque, backward torque slip, that is 2 minus s. Okay, so we will use that over here. Okay, so the total torque, then so the total torque is the summation of this forward torque and the backward torque. Okay, so if in the figure shows both torques and the resultant torque for slip between 0 to 2 at standstill, slip is equal to 1 and 2 minus 1 is 2 minus s is equal to 1. Hence Tf and Tb are numerically equal but being oppositely directed. Products produce no resultant torque. That explains why there is no starting torque in a single phase induction motor. That means as two same magnitudes um, uh, poles are generated, two magnitude two flux are generated, due to that two same magnitude torques are generated, but in that case it is in the opposite direction. So for that what is happening, it is neutralizing each other, so there is no resultant torque, so it is not self starting. uh, So hence there is a certain amount of net torque in the clockwise direction which accelerates the motor to the full speed. So this thing is achieved by uh, increasing any one of the torque or adding some capacitor or using by shaded poles. So different methods are there. So the resultant torque of the single phase induction motor is zero only at a slip of unity of the synchronous speed in either direction. Once rotating in either direction, therefore the single phase motor will continue to rotate in that direction because the resultant net torque is produced to the left or right of the standstill point. Okay, so now the point is that due to this nature, due to this concept, it is not self starting. The opposite torque are magnetically same torque magnitude. The magnitude of both torque has the same value, but it is not self starting, but as the direction is opposite. So how we can make that as a self starting machine? So a single phase induction motor is not self-starting. To overcome this drawback and make the motor self-starting, it is temporarily overcome by two-phase motor during starting method. So two-phase method is basically speed phase method. For that purpose, starter of a single phase induction motor is provided with an extra winding known as the starting or auxiliary winding in addition to the main or running winding. These two windings are placed 90 degrees electrically apart and are connected in parallel across the supply phase as shown in the figure below. It is so arranged that the phase difference between the currents in the two stator winding is very large. Hence, the motor behaves like a two-phase motor. These two currents provide a revolving flux and hence make the motor self-starting. There are many other methods by which we can do the same thing. The single phase induction motor, which is equipped with an auxiliary winding displaced in magnetic position iron and connected in parallel with a main running winding, is called split phase induction motor. So as we can see in the below section, there is a diagram. So in that diagram, a single phase supply is given. So there we have the um, starting winding, and there is we have the running winding. With the starting winding, we have connected resistance and there is a centrifugal switch. Okay, so when supply is on, so the current is flowing through the both coil and centrifugal switch is also closed. So there is a generation of resultant torque which has some value and some particular unidirectional force, so due to which the rotor starts rotating, and when it is achieving its rated value 70 to 80%, so at that time the centrifugal switch automatically disconnected from the system and the whole system runs on only on the main winding. Okay, in the right hand side we can see that there is a phasor diagram. So where this V is the supply voltage, this I is the current, in between that phi there is an angle. Okay, and there are two current, that is IS and IM. So what is IS and what is IM? IS is the starting winding current passing through, and IM is the current passing through the main winding. Okay, and that in between that two current we have an angle of alpha. So this is the speed phase, and uh, centrifugal switch is connected in series with the okay. uh, Yes. So now during starting method, when IM is large, relay contacts close, thereby following is to flow and the motor starts as usual. After motor speeds up to 75% of the full load speed, IM drops to a value that is low enough to cause the contacts to open. Okay, so that means very interestingly, we have I have placed this graph over here, that initially when is the percentage, this is in x axis we are considering the speed, and y axis we are considering the torque. So when the from a particular value of torque, after that the motor starts rotating. So when it is reaching its almost 80% value, okay, so what does it will happen, this Im current value is dropped suddenly, okay, so that the magnetization in the centrifugal switch can be neutralized, and it will be cause the contacts of that centrifugal switch be disconnected, and when it is disconnected, the the auxiliary winding or the starting winding also disconnected from the system. A typical and only depending upon the main winding the motor rotates, okay. So the typical torque speed characteristics of such a motor is shown here, obviously, that I am explaining, okay, right now. So this is the another type. There this motors often used in the performance preference to the costlier capacitor start motors. Typically applications are fans and blowers, centrifugal pumps and separators, washing machines, small machine tools, duplicating machines, and demonstrating refrigerator and oil burn, etc. Commonly available size ranges from 1 by 20 to 1 by 3 HP, that is 40 to 250 watt, with specific ranging from 3400 to 865 RPM. Okay, so as shown in the figure below, the connections of the starting while have been reversed. The speed regulation of the standard speed phase motor is nearly the same of the three phase motor. The speed varies with 2 to 5% between no load and full load. Okay, for this reason such motors are usually regarded as practically constant speed motors. Such motors are sometimes referred to as resistance start split phase induction motor, in order to distinguish from the capacitor start induction motor and capacitor start and capacitor run single phase induction motor. So this is all for today. So in this particular presentation, what we have studied that how the double revolving field is working and why this is not self starting, and then we have seen that how we can start this machine, what are the different methods we have by which we can start this machine. I think this is clear to you. So this is all for today. Thank you.